good morning. Welcome to Cosmic Conversations here on the Morrison Planetarium Facebook Live page. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the Academy, and it's a great pleasure to have our guest today for our final Cosmic Conversation of the year, Carter Emmart, Director of Astrovisualization at the American Museum of Natural History in New York City.
Thanks, Ryan.
Yeah.
It's a pleasure to be here.
Yeah, it's great to kind of wrap up the year with this. We've been doing these since, well, it seems like forever, but late May-ish. And so to kind of, for the final broadcast of the year, we're going to have sort of a global perspective on the universe, in a sense, and also the development of the software and tools that we use to visualize it. So I just want to introduce one person who's behind the scenes, who's going to be doing a lot of the piloting. Many people will be familiar with Josh. Josh is going to be mostly doing stuff to make sure that the flow of the program goes well. And then even more behind the scenes is Mary, who's producing all this. So we've got all hands on deck to give you a great conversation this morning.
If we crash into anything, I'm sorry.
Never apologize in advance. So yeah, actually, I mean, as we started to talk about this, I think what's interesting is that Carter and I both had agreed that there was this, and actually we can go back to that picture of the star projector from Morrison Planetarium. That one of the things that planetariums have always done in science visualization, it's just that they used to only visualize one data set, and that was the night sky. And that's true. The Morrison Planetarium projector, which was home built here in San Francisco, as well as the original Hayden Planetarium. And we started with the Morrison projector. We're mostly going to focus on the story in New York, but just to give a little background, we actually had a couple images here of the visualization process for the original projector. This is Leon Salve, who's on the right-hand side, who was the original staff astronomer for Morrison Planetarium. He's working with a professor from Cal on the state-of-the-art computer for 1950 to do the calculations involved with positioning the stars correctly on that star projector. And just to give a sense of what science visualization and data visualization looked like at that time, this is the almost 60-foot long printout of those star positions. And so we've come a long way in our new access to a digital three-dimensional universe, not just the night sky. And that's where I think Carter can talk more about the history of the Hayden Planetarium and how it evolved into the 21st century.
Well, it's interesting, Ryan. Yeah, we sort of have these two slides. This is nice. This is a picture of the Hayden Planetarium along the time it was built. So it was 1935, and then let's see.
Sorry, I didn't mean to.
Going back to data, which is great.
Yeah, always goes back to data.
Yeah, and you can kind of see, even though it's a dark night image, this style to the planetarium. It wasn't embellished too much because it's actually sort of a courtyard within what was to be finished off, sort of a section of the museum along 81st Street. But it was well loved. I myself started taking classes there when I was 10 years old. My mom used to drive me in. It's in fact my mother's 96th birthday today. Yes. And so we could see the surrounding museum, but in the next slide, we see what was built in its place. And that's nice. Thanks for doing a cross dissolve there. We can see that the planetarium sort of stayed in the same place. However, it was completely torn down, but rebuilt in place as the Rose Center for Earth and Space. And really the call of this was to go from a planetarium showing the sky to using modern methods to go into the sky and really experience almost kind of like a spiritual quest in a way, the totality of the universe and what we've come to know of it. However, depicting that with all known measurements, so thus data visualization.
And AMNH was really a pioneer, the American Museum of Natural History in the 21st century. Hayden Planetarium really pioneered this because I think a lot of places had started to build this, but at AMNH, you really built the infrastructure to do this as a basis of visualization.
Yeah, and it's when I first heard about the job, Dennis Davidson, who is sort of my predecessor, is an artist at the planetarium. And planetariums always needed artists to depict the various other worlds and so forth, but using techniques of scientifically informed artwork And our job was one to really look at data visualization. And Dennis told me that the goal was to make a model of, to make an accurate atlas of the universe and be able to fly through it in real time, kind of like a giant flight simulator. And in the mid 90s, when I heard that, although there were some technological analogs, they're in very early state. So this is a high mark, but we achieved that, and that's what the software is, OpenSpace, that we're going to talk about. And so this, the rebuild was a millennium project. I joined the team in '98, but we opened in 2000. And Ryan, you also joined us there in the year 2000. So
right.
We have this common lineage going back. So.
Exactly. Well, now, although we're going to go all the way out into the universe and out to the cosmic microwave background in the next half hour or so, the story actually does also really start at Earth and the kind of complementary research efforts at NASA's Science Mission Directorate.
Yeah, so OpenSpace is a NASA-funded, open source, interactive tool, and it's a data display, but really a data visualization. I mean, everything it's showing is visualized data. We show this slide here, which is nice. This is NASA's worldview. Has over 100 different layers that are collected, are being collected. So the reason that this is an incomplete map, where you just see a ghosting of lines for the Americas, is that, I grabbed this image yesterday on December 17th, is that the particular mosaic of satellite images is not finished for this particular layer. And so we wanted to be able to take these maps, stream them into OpenSpace. So I think at this point we can go into OpenSpace and look at that. So, and Josh, thank you. Josh is flying this for us. We'll zoom in here, which is nice. And Josh is just even showing the interface. This is great. OpenSpace is available for anyone for download. You need a pretty good graphics card, or if you're a gamer, you have a gaming graphics card that's going to work. My Mac, 3-year-old Mac, this works fine. But from OpenSpaceProject.com, and you can obtain it. And so it's also an international collaboration. In the year 2000, right after we opened, I had the great pleasure of meeting at SIGGRAPH Anders Innerman, who's one of the world's leading data visualization academics, and he's at Linköping University in Sweden, about 2 hours south of Stockholm. So we saw the museum there for a moment. We're backing out. We see Manhattan, of course, our home here, and thanks, Josh, for flying us down and back. But when we got NASA funded in 2015 to build this out, we partnered with the University of Utah and also New York University. And so that enables us to have about half a dozen professional developers, but a lot of this has been developed by student work, and so a series of student thesis projects. So we saw the Earth. One of the things is also the atmosphere, and so I'll just say a moment for the Earth. The Earth is beautiful, as of course in 1968 when we first got to the moon and looked back at the Earth, that famous Earthrise picture, was that we had this perspective. And to do this properly, I showed you that Earth map in the slide, but we also have a physics-based atmosphere. I think what I'll do now is, if we can go and share my screen for a second, we're going to now just move over to, I'm controlling this, and this is the International Space Station. It's standing still, but if I just hit the go key, we're now moving. Doesn't look like it, but we're moving at 17,500 miles an hour, 250 miles above sea level. And we're flying over the data that Josh is showing you, but I'm from yesterday. So I'm just kind of looking at that, but we see the space station. This is NASA's model. So we can zoom around it and show you the various aspects of it. There are 11 countries participating in the International Space Station. It's about a football field in size if you account for those solar panels you see. And the space shuttle, which brought in all the very obviously cylindrical experiment modules, and these, in fact, right here are the Japanese experiment modules. Over here is the European Columbus module. On the back are the Russian modules, Zarya and Zvezda, which were the beginnings of the space station up to the top there, as we see now. But over 100 launches of the American space shuttle to bring up the various components and build this. This is just one model that we can sort of bring into open space. I wanted to just emphasize how thin the atmosphere is. So we're doing this, by physics. So we're showing the atmosphere scattering properly above this Earth image. And so the Earth's atmosphere is only about 20 miles thick, 30 kilometers, where it trails off to black. It actually exponentially dies off. And so the atmosphere it may not be visibly detectable, but it continues sort of on up at a small amount. So here we are orbiting.
It actually creates drag on the ISS, right? I mean, it's like the ISS has to be bumped up to higher orbits because there is just enough atmosphere to cause drag.
That's right, and so even orbiting 250 miles up, and I mentioned how the atmosphere seems to go to black at about 20. There's enough atmosphere. That's right, Brian. That causes a significant drag that over time would bring down the space station. So that they go to that. I'll just mention this seems like, well, we're high up above the clouds here, but if I just pull away from Earth for a moment, this nice image that's gathered by multiple passes around the Earth to build up this mosaic daily, is that I can also just invoke here the other satellites. Going around the Earth in low Earth orbit where the ISS is, we're in close, so we're feeling the gravity more of Earth. It takes you only 90 minutes to go around the Earth at that altitude. Farther out, the effect of the gravity is felt less, so we actually orbit slower. This prominent equatorial band of satellites called the geosynchronous satellites are such. They're geosynchronous because they go around the Earth in 24 hours, which matches the rotation rate of Earth. This distance is some like 23,000 miles. And that is 1/10 the distance to the moon. The moon is about 240,000 miles away. So it's almost 1,000 times the altitude of the International Space Station. And so we can see here, how small the Earth looks from this point, and the moon is 1/4 size of the Earth, so it's quite far. Ryan, I know you have this slide, so I think we may now go to this. This is a favorite map of mine. It came out when I was 8 years old when we flew to the moon. So this is the 1969 National Geographic foldout, and I call your attention to the bottom of the map. We see a small Earth in the lower left corner, and over on the right, we see the moon, and they are properly scaled in size and distance. And you can see, yes, they are diagramming the trips of Apollo going from Earth orbit out to lunar orbit, to lunar landing, and so on. But I remember staring at this as an 8-year-old and thinking, wow, the moon really is far away. In fact, it's so far, you could fit all the other planets, including Jupiter and Saturn, Uranus and Neptune, in the distance between Earth and the moon, which is quite an amazing notion. So I think before we go on, I just wanted to mention that the funding that OpenSpace gets is from NASA's Science Mission Directorate. And Ryan, you began to talk a little bit about that. I just wanted to emphasize that the science division of NASA is organized into sort of 4 main groups. And so we have Earth science, planetary science, helioscience, and that's studying the sun, which of course is the very important star that we live next to, or orbit around, and then astrophysics. And so out of these 4 divisions, OpenSpace our call is to visualize science in those 4 divisions. So I think Josh has keyed up here.
Before we leave that image, I was just going to say the interesting transition as you look at this image, which is beautiful artwork, but it kind of goes to that same message that you had around Hayden Planetarium transitioning to the modern era. We're going to transition now from this beautiful artwork to data-driven visualization of all the remarkable data that's come back around Earth's moon and the reconstruction of the Apollo sites.
That's right. And so what we're going to do, and Josh, just before we do that, okay, I was wondering if you might be able to turn the shading of the moon off, so we might see the entire moon just for a second, if we can.
So in a sense, that same perspective we just have, but not flat, but in 3D.
Exactly. And thanks for making that point, Ryan, because the map and the image of the moon we see here, in a similar way that we depict the Earth with satellites, and even when we came in close to the Earth, we were looking at not so much NASA data, but satellite data that was pulled together by a company, Esri. And let's see. It's okay if that doesn't work, Josh. My apologies if let's see, moon, and yeah.
We had a question. I think it was just confirming what you had said before about about fitting all the planets in the solar system without leaving a gap. So, not sure.
That one down there, perform shading. No, below that. Yeah. Okay, there you go. Yay! Cool. Thanks, Josh. It's always tough to sort of present and fly, and so Josh did a great job.
Josh for being the.
So when we looked at the moon, even through telescopes, we could tell that there were mountains. We could see there were circular holes, and then there was a debate whether they were volcanic or impact craters. We now know they're impact craters. The smooth areas are really smooth. I mean, they're darker gray. They are lavas that up well after giant impacts. But of course, we landed in something with Apollo 11 over in the flat Mare Tranquillitatis. So Sea of Tranquility next to Sea of Serenity. And between the Sea of Tranquility and Serenity, it all sounds very nice, it's a dark sort of lava area, the landing site of Apollo 17, which was the culmination of Apollo. And we want to bring you in and just show you that, so show this capability. We'll zoom in on this. And so Josh is centering us on that, very nice. And we're now going to come into this valley deeper than the Grand Canyon, the Taurus Littrow Valley, and we have a special map that's sort of loading here. It was prepared from Lunar Reconnaissance Orbiter images, mosaics together, blended beautifully, and then labeled. It's a collaboration between NASA and the U.S. Geological Survey and the German Space Agency. And this shows color-coded different trails where the astronauts drove the lunar rover. And so they landed in this light gray area. In fact, within the light gray area, which is our close-up, we can see a lighter patch with a dark little thing in the middle. And that dark little thing is a lunar module, which is about, we'll see in a moment, it's about 20 feet high. And but as we get in close, the Lunar Reconnaissance Orbiter, with its narrow angle camera, so think of a telephoto lens orbiting the moon, it has a wide angle camera that sort of maps the entire moon, but then we can come in even closer to this guy, and we're going to see the foot trails. We can already see a combination of both the tire tracks of the rover, but the sort of more random walk or foot trails of the astronauts back and forth to their science experiments on the left. The LRV, you probably see that over on the right, that's Lunar Roving Vehicle where it was parked. And so we can actually see the geostation and the foot trails of the astronauts. Pretty amazing. I'm not, so anyway, we'll pull back.
I have a question coming through about whether we can go down to ground level on the moon or Mars in open space. So we're almost there. I don't know if it's possible to go kind of make the dive all the way down here, but
are we going to go over to Station 6? I'm not sure if we had. Well, let's see. We're going to come down here first. And the beauty of this, what you're seeing here is terrain mapping. We're seeing the mountains. And so we basically have sort of two types of maps. We have one which is this mosaic of the images from the Lunar Reconnaissance Orbiter. And Station 6, we actually see what looks like a boulder trail, a rock rolled downhill, and And so this provided a geologic sample from higher up on the hills of the moon. And it rolled down, it broke into 3 pieces. And we're going to fly up now to some photogrammetry. We can now do this on like the iPhone 12. Just take
right.
And but in this case, what Josh is showing us is photogrammetry that was done by Sham Tagaraja, one of my high school students from the Bergen County Academy's high school. And what we used as source images were the pictures taken by Commander Gene Cernan, along with Harrison Schmitt, the only scientist to ever go to the moon, Jack Schmitt, and who is still alive. He's still with us. Gene Cernan passed on a few years ago, unfortunately. He was a very nice man. Got the pleasure of showing him this at one point. But here we actually see, we can even come closer, Josh.
And so the technique here is that with photogrammetry, you use multiple images of the same object or same location, and then basically using computational magic, what really still seems to me like you can reconstruct based on those different camera angles, you can reconstruct something in 3D, which is what you've done here, except with rather than with new images, with images that are nearly 50 years old.
Yeah, and so one thing that was very nice is that Flickr actually put together a beautiful thing. It's called Project Apollo Archive. Go there, check it out. It has every picture of the astronauts.
Oh, very cool.
And so with that, we could actually do this reconstruction. So I think we want to show a couple other things in OpenSpace. Boy, I wish my presentations tend to go hours and hours just because there's so much to see. But
well, there is the entire universe, so you figure
we got a lot of ground to cover.
Yeah. But so, I think our next step then is heading to the sun.
Yeah. So just as, our sky, of course, to talk about sort of a traditional planetarium show, is dominated by the sun, moon, and stars. And so we see the starry backdrop. And now we're going to show you our sun. We're going to fly up to it and look at something that OpenSpace, when we started talking about it, Professor Inuman and myself, there have been previous softwares. I don't need to go into that, but we wanted to really concentrate on making something that was open source. We were, it was a great honor to be awarded the NASA grant that has helped us develop this. But we wanted to show dynamics. Here's our sun. How about solar physics modeling? This is a very important facet of NASA. NASA observes the Earth and climate change, of course, but also what drives the Earth's climate is the sun. And the sun's quirkiness, it has a solar cycle of sunspots and activity on about 11 years. There's also a 22-year cycle of that. But what we see here is a simulation of activity on the sun. This is from a group called Predictive Science Inc. out of San Diego. And so what you're seeing here is a concerted effort of development of OpenSpace with NASA's Community Coordinated Modeling Center at NASA Goddard. And then also in collaboration with this Predictive Science group, Predictive Science Inc. And so what we're seeing is a solar flare that took place in 2007. And we're seeing the simulation of this event that was carefully controlled so that it mimics as best as possible to observations that were made Bastille Day, July 14th of 2000. That may seem like a long time ago, but there was a whole series of observations from satellites and ground base, which is a treasure trove to look at simulating this event. And what I'd like to do now is back off a little bit. We're in close, so if we go out, there's another modeling and also from another timescale, actually from 2012. And
goes to your point that, whereas you see the Earth's atmosphere and it looks like it peters out, we think of space very often as being empty.
Yeah.
But in fact, the sun is constantly spewing out a stream of charged particles. And because of the sun's magnetic field, you have this interaction between the charged particles and its magnetic field. So I think the lines we're seeing here are the magnetic field lines, a representation of that. And then combined with the observations of the density of the solar wind in the material from Wright.
That's right. So we see the field line traces and then color coded conveniently to show that density. And we've also done another thing. We've limited the field lines because they go off in all directions, really.
Right.
But we've limited them to sort of the plane of the solar system. We refer to the ecliptic. That's the Earth's orbital plane, but all the major planets, align pretty much with that plane. So we're seeing this event, and Josh, if we could pull back a little bit, please, and I'm not sure if we see the orbits of the solar system in there, but we'll be able to dive down to the Earth in just a little bit. Where you see blue, oh, that's nice, is that we're actually seeing the highest density. We're seeing a coronal mass ejection event. And in this case, let's dive into the Earth now if we could. And the Earth, of course, also has a magnetic field. And the dynamics, the interaction of the Earth's magnetic field with that of the sun's, what we call the heliosphere, helio for sun, leads to this dynamic we call space weather, and that affects, of course, us on Earth. We may have had an issue with that.
One of Josh's graphics card here. I'm not sure.
Well, I think we might just be there, Josh. If we pull back a little bit, might still be there. Oh yes, we just came in too fast. That's okay. So there's the Earth, and boy, what we're looking at there. We're looking at New Guinea, and then we're pulling off, and now we see the effect. It almost looks like a sea creature of this dynamic. We see flow lines of the solar wind. These are the streaming of particles, and Ryan, you were talking about that. Mm-hmm. And they blast past the Earth's magnetic field, making it look aerodynamic. So it actually shapes the Earth's magnetic field, and so then this interplay. All these lines are this interplay of field lines between the sun and the Earth. So OpenSpace, as I was beginning to mention, from the very beginning, we wanted to show dynamic simulations of astrophysics. And so this is heliophysics, to be particular, but it's really astrophysics. It's how stars behave. And we have a star right next door that we rely on. Exactly. So no better place to study a star, but from 93 million miles away from one.
Well, it's just so spectacular because it's so fundamentally, I mean, four-dimensional, but three-dimensional in terms of the nature of the structure of the field lines, and then how it changes over time. You really need a tool to see what's going on, because it's it's just not very easy to do it with a lot of two-dimensional charts or numbers. Yeah.
Well, this simulation goes out from one Earth distance, we call an astronomical unit, 2 Earth distances is just beyond the orbit of the planet Mars. So of course you see Mercury, Venus, Earth, and then Mars. So we're going to go to Mars now, and Mars is an interesting world, red in color because it's rust that we've come to understand. This is giving us this red color. It was the god of war because it was blood red in the sky. We see some red stars too, just passing one back there. Well, that's a star Arcturus. It's more yellow, but anyways. As we come up on Mars, we've done a lot of mapping with Mars. So right here, this is a very detailed map. Doesn't look so great from here. There are other maps we have. I'm not sure. We might just show you one, maybe the Viking map, if it comes in. Let's do the Sweden one, maybe. Yeah, I think the Sweden.
It's a problem with data visualization that sometimes when you visualize data, it doesn't always look exactly the way you want it.
Well, also, I should emphasize that what's happening here is pretty amazing. While we started out talking about the Earth and we had maps from NASA, we're actually streaming that data live. And so what I've asked Josh to do is bring in this other map. But let's forego that. Let's come down to the canyon if we can, Josh. And what we need to do is rotate Mars. Yeah, just let's rotate about 12 hours. And we should The canyon is currently on the night side. So I'm asking Josh to do 1,000 things at once, which I know if I was flying, I'd be going, oh no. But anyway.
It's a great introduction to the interface of OpenSpace.
Yeah. So, and the interface is part of the fun. It's a challenge, but in fact, there's some tutorials I've done. I'm going to be doing some more. We have a new release that just came out. But if we continue going a little bit, keep rolling. And then, the Valles Marineris is, let's rotate Mars even a little more into the sunlight. Or right there on the terminator, the difference between night and day is we're getting close, and then Josh can adjust time so that we'll illuminate a little more. Is the fantastically huge canyon, which would stretch from New York to Los Angeles, but it's on Mars, which is half the size of Earth, which means it's twice the size of the moon, but smaller than Earth. It has an atmosphere. It looks deceptively thicker than it is. It's actually equivalent to about 100,000 feet on Earth, and but it's dust laden. We're going to come into this canyon, and the canyon walls are not like looking at the San Gabriels if you're in LA, where those are maybe about 5,000 to 7,000 feet, which is impressive enough. But as we come down, let's see, is our height map on, Josh? These walls of this canyon are right here on the order of about 20,000 feet tall. And so, let's see. Try turning on MOLA.
And I think a good comment to make here too is you see these sort of patches of large rectangles on the surface of Mars, and it's not like there's cropland in the Midwest where you've got this is transitions in some of the layers of data, and you can see that from orbit as well. So it's a kind of, I think it's a nice way of illustrating that these are actual data sets. This is not just Hollywood magic or anything. This is really using data at different resolutions to be able to come into this view.
And even though our height map may be failing, and that can be a combination of just Josh is at home, and that this is internet service, and we're asking a lot of data to stream, especially for this presentation. But Josh, if you could just get close to the edge between these two data sets, and Ryan, just to your point, the surrounding global data set is about 5 to 7 meters in resolution, and then if we get really close, we're seeing, oh boy, the map before it disappears. I know what version of OpenSpace you have. Okay, so we can pull back away from this, but suffice to say that high resolution of wind-carved layering we see in the canyon is only about 10-inch resolution. It's amazing. Why so high res? But if we're interested in landing on Mars, as we did with the rovers, we needed support from the orbiters, in this case, the Mars Reconnaissance Orbiter, to get down to the size of a boulder that might be a bad day for your rover. So we are seeing fantastic things. Inside these canyons are layers. What were these lakes? We see ample evidence for flowing water on an ancient Mars, billions of years ago. How do we know that? We haven't even brought samples back from Mars yet. But we can compare what we see on the moon to the sort of cratering record on Mars. And we certainly see that Mars has a way thin atmosphere today. But in the ancient past, around the time life was evolving on Earth, that Mars seems to have been much more clement and Earth-like. So
that's very cool. Well, and those are the results of some of the exploration that NASA has done. But one of the other cool things that OpenSpace does is it reveals the way the missions actually proceed. And I think we have a video that shows something that was developed for the New Horizons mission to Pluto.
Yes. In this case, what we see is Pluto with a map that was taken earlier in this flyby sequence of July 14th, 2015. And so what we're showing, what's moving around, we see a frame and lines from it. The spacecraft is behind us. But from the spacecraft, and we've zoomed in closer to the target, Pluto, sorry,
Right.
it's talking about Mars, is that we actually see the footprint of the camera. And then what we do is take the image that was sent back and image project it to the geometry of Pluto. How do we do this? This is an interesting interplay between the targeting and tracking of NASA satellites. And we know exactly where they are by using the radio communications with the Deep Space Network. So we can see exactly where, say, from the Earth perspective, where a mission is in the sky. And then we use the round trip time of radio light to know exactly the distance. And in this way, we can track satellites highly accurately, and we can plan missions. And there is a navigation system that that NASA puts out, and it allows us to take that information into OpenSpace and dynamically preview or reconstruct what exactly happened. So this really shows a combination of not only the geological discoveries. We're looking at Sputnik Planitia. This is a basin filled with a slushy nitrogen sea, and these dark areas of tholins, which is ultraviolet light of the sun interacting with a sort of exotic organic frozen chemistry out of Pluto. But it shows you how we do what we do. And it's amazing that we see the results of these as maps, but it's I think equally amazing to actually see how NASA goes about this. In this case, we see multiple frames. These are different instruments that are doing different observations, and we're concentrating just on the camera results. So I think in this case, we can probably move on from this, but
well, it's cool. And speaking of maps,
yes.
we're now going to transition to going outside the solar system and to the universe beyond. And this was a great example of kind of, again, sort of how it started versus where we are now. And this, I think, from the Norton Star Atlas.
This is, yes, the Norton Star Atlas has long been a favorite of mine, ever since, taking classes at the planetarium when I was not even in high school yet. And my friends and I would freeze in the backyard looking up through our telescopes and stuff. But we'd use star maps like this. We didn't have computers in the 70s to guide our telescopes. And what we see, there's a constellation Orion, and there's spot sizes, like in this case, it's got a negative image. So we see bigger black dot for the brighter stars. And up top, there's a very important thing, which is the stellar magnitudes up there, and that's being pointed out. Thanks, Brian, and pointing all that out. And also, we see the Orion Nebula. There's a close-up on the map, and all this great stuff. Well, in OpenSpace, we had to draw what the sky looks like. Now, we all know the stars are at different distances. I mean, they're not all just stuck to a sphere out there. I mean, there was a big debate about that until we actually began to get stellar distances. But we now know that we live in this thing called the Milky Way galaxy. We'll look at that in a second. But let's actually look at translating. Let's look at the sky in OpenSpace now.
Cool.
And what we're going to do, Josh has keyed this out. This is nice. And we see that line is sort of the solar system. There's the Milky Way, and it has that weird pattern there. Well, that pattern actually is a set of stellar apparent magnitudes. And what I mean by that is how bright stars are. And we created a three-dimensional matrix. Now, we also see the real stars. As we pull away from the sun, we're going to see the solar system swallowed up into the light of the sun. And you'll see that this test target, which was computed by my colleague, Brian Abbott, who maintains this digital universe, which we're now looking at, this accounting of stars, galaxies, and zoo of objects that make up the Milky Way, is that we needed a discrete, reliable test source of stars at different distances and different brightnesses. Imagine you're on the one side of the Golden Gate Bridge, and you're looking at a searchlight in your eye. It's going to be pretty bright. But then somebody switches it to like a night light bulb. You're going to barely be able to see it. stars come in various sizes, and Josh is doing a great job right now. We were looking around and see there's some bright stars. We see they're dim stars. Way down in there is a very dim star that we call the sun, and we don't even see it from wherever we are. But and that leads to this conundrum of sort of, where are we? We've gone out into this data set. What is this data set? In order to make shows about space, not just about sky in the planetarium, we had to create this atlas of stellar positions in true space. So we would see where they are on the sky and get their distances. But we also had to account for their brightness. Josh, can we fly in just a little bit closer for just a second? Thank you. And there's the sun. So let's do this pull back just a little slower once again. And that first star that starts to move is over there just to the left, Alpha Centauri. It's really a triple system. The brightest star is about the brightness of our sun, 4 light years away. Now joined by the star Sirius, 10 light years away. We are looking at light that, it takes light, it goes at 186,000 miles a second. But it takes light 8 minutes to go from the sun to the Earth. And here, the nearest star is 4 light years away. So here are stars in this neighborhood right here. This is the Hyades star cluster Josh has just flown through. That's 150 light years away. And so in this way, we can atlas the universe. Let's do the pull out to the Milky Way now. This is nice. And as we do, notice that there's a bit of a transition, that we begin to lose the stars. We're coming up now with statistical stars in a simulation of the Milky Way that is based on observations of gas clouds with radio light. And this simulation was done by our colleagues at the National Astronomical Observatory of Japan in Tokyo, and also Tokyo University, and Baba, Wada, and Saito. And so we worked in developing a visualization of the Milky Way from the best source. What they did was run a simulation to then basically merge that simulation with the observed results. And that's what we see. The Milky Way is such that we live halfway out, about 26,000 light years away. Could we turn on the orbit of the sun, Josh? I'd like to, oh, that's awesome. That's just great. And just as we go around the sun goes around the galaxy. And it's in a fairly regular orbit. It varies a little bit. This is a simulation by Sebastian Levine, one of our astronomers at the Rose Center, or was with. He's now somewhere else, but he was with us for a number of years. And this shows our orbit. We go around the sun in 1 year. We go around the galaxy in 250 million years. And the last time we were in the position we are in now, the fauna were just starting to crawl out. Think of mud skippers. They were just starting to, come on land. 2 turns back, the first pioneering of land by plants. And all life before that, is they were talking about the sort of Precambrian and everything. It's about 2 turns back. Is that right, Ryan? So
yeah, I mean, Precambrian would be just a little over the 2 turns back, and then
yeah.
So.
And if you look at the oldest moon rock, 400, about 4.5 billion years old. So we've been around the block here about 18 times. The last time we were, well, if we just go a quarter turn back, is when the dinosaurs died off.
Right.
This nasty asteroid hit us in the Yucatan. But let's actually, if we have time, I'd like to pull away from the Milky Way.
Sure.
There have been other presentations here that talked about exoplanets. There are about 200 to 300 billion stars that make up our Milky Way galaxy. As we pull out, we'll see the galaxy return here in a second. So let's keep going. And let's keep going. Great. And now we're in this realm of galaxies. And the nearest galaxy, Andromeda, it's just about 2 million light years away, a major galaxy. We have some smaller ones orbiting us in Magellanic Clouds. But we're now looking at a realm where we're tens to hundreds of millions of light years away. And every one of these points is a galaxy like us. Every one is several hundred billion stars. If you do the math and extrapolate the exoplanets, we're now finding almost all stars, it seems. Easily 1 trillion worlds for every point. We move out far enough, we come to a deeper survey here, the Sloan Digital Sky Survey. There are other surveys that we can augment this with, but this truly shows this scale of the universe, and brought to you in a software that can take you from, you know, the buildings of Manhattan where we started, all the way out now to these farthest galaxies we've charted. The farthest ones are really the quasars, which are very bright galaxies. So far away, we're looking at them like baby pictures of what they looked like billions of years ago. And we see around us the present. But if you look far enough away, you're looking deep, deep into the past. And behind that, there's a bit of cosmology that I won't attempt to fully explain here, but this expanding universe illustrates that we must have been expanding from a time of great density and a time perhaps setting the universe free from this Big Bang. And so here, mapped by the Planck satellite in 2013 is this stipulation in slight temperature variations. Ryan, I don't know if you want to speak to this.
Oh, yeah. I mean, I think that, you know, as we saw those clumps and clusters of galaxies close to home, this is really the origin of that structure that we see. By structure, I mean the clustering of galaxies, and that where the little bright spots here represent hot spots in this sort of baby picture of the universe. And the dark parts are cool spots. But like you said, that's a tiny variation. We've cranked up the contrast on this image. So the hot spots are only about 1 in 100,000 parts hotter than the cool spots. And eventually those hot spots would evolve into kind of regions where there aren't many galaxies. The cool spots would kind of condense to form the clusters of galaxies and superclusters of galaxies that we see in the nearby universe. So this is like the blueprint that ends up forming the remarkable structure that we see today. So
I'm wondering if we have a deep survey in here. If Josh, I'm not sure if that made its way in. I know Dantel worked on it.
Yeah, I don't think that was. I don't think we added that, but yeah, that was a pencil beam view out into the distant universe where we looked at individual galaxies. And yeah, unfortunately, I don't think we have that.
And that's okay. I'll just mention that kind of a preview to this telescope that's to be launched in hopefully in October of this coming year, the James Webb Space Telescope, and it's larger than the Hubble, and is designed to really see in infrared light. So the farther and farther we look away, this expanding universe causes the light to be more and more red. It's from the Doppler effect, and so it's designed to really look deep into the universe, into realms we've never seen before. And so in kind of this notion of as far as we've looked today and seen and plotted in this way, is that we're going to this upcoming year is an exciting time for new discoveries, really.
Yeah.
And what I love about this, and I mentioned in the beginning, an almost spiritual quest, in a way, to see this not as artwork, but as to know that this is done in a rigorous manner from real measurement. And it's a real map. We call this the digital universe. There are tons of other data sets that can be turned on to show, say, the structure of our Milky Way and different objects within it. But those are subjects of the various conversations that you've had with others and will have in the future. So,
yeah, well, I think it's great to kind of bring it back to where we started. That, you know, that original planetarium from the 20th century, showing the static night sky in some way. Those really for a human lifetime, the lifetime of culture, the unchanging patterns of the stars. Whereas, you know, what this reveals is not just a three-dimensional universe, but really a universe about which we're constantly learning things, and that we're catching at these moments of change. So I think it's a great illustration of how this leverages our changing understanding and our new perspective on the universe around us. So thank you.
There's sort of a comforting notion. before my father passed away, I remember we were talking about my grandmother, who I never met. My dad was 17 when she passed away. And I limited the stars in distance such that we were looking at a shell of stars that represented that the light that we're seeing now is coming to us from within her lifetime. So, she was born in 1888 and died in 1940. And so you can do that. And in this way, I think the universe, it speaks to us in a way that we see the stars, we can't reach them, the celestial realm, and we sort of understand that beauty of nature in this way. But in a real sense, that we see the universe across the ages of it. And the most beautiful, the most colorful planet that we know of is Earth. And we know that it's colorful because of the scattering of the blue light from oxygenated atmosphere that was created by life, the green of life, the browns of the desert and geology, and then the whites of the clouds and the ices, that we live in the garden planet. And I just hope that that it remains that way.
Absolutely. Well, I think we've more than used up our time for this morning. I don't know if we had any more questions coming to us from online, but I will note that you queued up a great topic that we're actually going to be running a repeat of a conversation next week, but it's a conversation that we had about astronomers for planet Earth, a group of astronomers who are thinking about how the work that astronomy does offers context for the efforts that we need to make here at home to maintain that beautiful, colorful planet that you so eloquently described. So, well, I don't see any questions. So with that, thank you, Carter. Really appreciate being able to spend some time with us on this last Cosmic Conversation of the year.
Well, thanks, Ryan, and thanks, Josh, and thanks to the whole team there. It's been a pleasure, and it's really great that you guys are using OpenSpace. I'm wearing the T-shirt. But download it yourself, openspaceproject.com.
Yes, and that will definitely be in the chat, both on Facebook and on YouTube, because actually I forgot to mention that we're also streaming this to the OpenSpace YouTube channel. So thank you to both audiences, Facebook and YouTube, who were joining us today. We're going to end. We started at the American Museum of Natural History in New York. We're going to end here at the California Academy of Sciences, currently closed to the public, but hopefully soon welcoming visitors again. And until we are open with the planetarium, we're going to continue running this program, so as well as our other live streams. So again, thanks, Carter, for joining us. Thanks you, Josh, for piloting, because that was a lot of work. And thank you, Mary, for producing. So,
yeah. All right.
Take care, everybody. Have a happy holiday season.
Happy